Chapter 4. Last time we covered we covered what the basic idea of a force was, but then we also covered Newton's first law. You remember what Newton's first law said?
It's at rest, you stay at rest.
That's right. Is that what you were saying, Brooke? If it's at rest, it'll stay at rest. If it's moving in a straight line and there's no external forces acting on it, it will stay moving in a straight line at a constant speed, velocity, however you want to say it. It's essentially the things we'll keep doing is what they're already doing as long as something doesn't make them do something else, right? And this is related to a specific thing about objects. What is that thing? Well, inertia is the name we give to this idea, but what is it that causes inertia?
Force.
Not force. Force changes things. It changes the movement. It can stop things, it can start things, it can turn things.
Just energy thing?
Not even, well, I mean, you could say energy, but you don't know enough about energy to say that yet, so. Unless you've been reading 12 chapters ahead, I'm not going to allow that answer. It's mass is what it comes down to. It's actually just the mass that determines this. Now I'm going to try this again. I used to be able to size this down a little bit so that the people who are watching the recording of this screen could actually see. I don't know, I can't make it any smaller. This is too big to look at. Anyway, so it's mass. What it comes down to, inertia is caused by mass. So if you have more mass, you'll have more inertia. If you have less mass, you'll have less inertia. And that's what it comes down to. So what is mass?
Not size.
What's that?
It's not size.
Mass does not necessarily have anything to do with size.
Density?
Its mass and density are related to each other along with the size. Exactly. It's just simply said, it's just how much stuff there is, right? How much matter. We use the word matter in physics to say stuff, right? But matter is just stuff. It's just how much stuff there is. And the reason that we make that definition very explicit is because people often confuse mass with weight. Weight and mass are not the same thing. Although weight measures the amount of force that gravity pulls on your mass with, it is not a measure of the mass necessarily. So, for example, I have a mass of somewhere between 90 and 100 kilograms of mass. That's a measure of how much stuff is in my body. Okay? Now, for everybody in that room, that doesn't really mean something for people in this room except for Milos. Milos knows that 90 kilograms is a little bit heavy for a guy my height. I need to lose some mass, in other words, right? But I'm not saying you would say that to me, but 90 to 100 kilograms, I should have a mass of about 75 to 80 probably. So I've got a little bit extra mass on my body. However, in the United States, we would equate that to some kind of weight, which it's not really equal to. But on Earth, gravity pulls on our mass, pulls on each kilogram of mass with a certain amount of force. And force is measured in pounds. Pounds is one of the units of measure for force. For every kilogram of mass that I have, at this elevation, gravity is pulling on me with about 2.2 pounds of force. So if I weigh about 90 kilograms, if I have 90 kilograms of mass, I'm going to weigh about 200 pounds-ish. somewhere in that range, okay? Where I should probably weigh around 170. So my mass should probably be around 80 kilograms, right? And that's the difference. Your mass doesn't change if you go to the moon. So if I went to the moon, my mass would still be 90 kilograms, but my weight would be significantly less. My weight would be right around 40 pounds on the moon, even though I still have the same amount of stuff in my body, right? So the weight depends on how much gravity is pulling on your mass. Your mass just depends on how much stuff you have in your body, right? Mass doesn't change, weight does. So you can't really weigh an astronaut on the International Space Station. On the International Space Station, the amount of gravity that they feel is almost zero. They don't really feel any gravitational pull. So instead of trying to measure their weight by using a scale, they measure their mass. Well, how would you measure the mass of something? Well, what you do is you measure how the mass reacts to forces. Because we've already said that force changes what a mass is doing. If a mass is sitting still, then a force will change it from sitting still, an external force, right? If a mass is moving, it will change. A force will change its movement. So let's go see how mass is measured on the space station. No, let's not watch volleyball, although volleyball is really cool. Okay. Measuring mass on the space station. So here it is. So they're saying, how do you weigh yourself in space? But that's actually an incorrect question. What they're going to show you here is how we measure mass on the space station.
We often get the question, how do we weigh ourselves in space? Well, if you have been introduced to physics, or mathematics, perhaps you're in college, or you will be in college, and you're introduced to calculus, you'll hear about the differential equation, and that's typical equation is the string mass vapor equation. If you know the properties of the string.
Okay, so he's going really into too much detail. This could be explained a lot simpler. This little blue thing in front of him is essentially a spring scale. Okay, it's got some springs on it, and when you put your weight on it or your mass on it, it's going to stretch or compress depending on which way gravity's pulling you. But on the space station, gravity's not really going to pull on you any differently than it's pulling on the chair, so it's not going to do anything. So let's see what he does with it once he's finished explaining all this crazy math here. He's going to explain the device here a little bit.
Physics, and that's what we use here. We have this machine here that's got a known spring constant and a known damping ratio, and we've got it set up here, and I'm going to release it, and you're going to see it's going to oscillate at some frequency here, and we're going to go through a calibration.
Okay, so that's the spring. So what he's done is he released it so that the spring starts bouncing. So instead of like the scales that we use today, I've got a great scale here. I found this scale at the second-hand store. I just had to have it. This is the kind of scale that was in bathrooms when I was a kid. Leftovers from the 60s and 70s, this green fuzzy thing. This scale has a spring in it, but we use the spring by stepping on it and compressing the spring. As the spring compresses, it turns a little dial, and it tells me that I weigh too much, right? So then I get off of it, that spring re-expands, and it goes back to zero. On this one, though, you can't step on it and make it compress. So what they do is they start it bouncing. Instead of coming up to this and just standing on it, they whack it with something and it starts bouncing. Okay? Now, springs bounce with a certain frequency, depending on a couple of things. It depends on the spring, and it depends on the mass that's on the spring. So that little blue chair is the mass that's on the spring right now. And they've got it wiggling back and forth, and they know exactly how much it's going to wiggle, how fast it's going to wiggle back and forth. They also know how long it's going to take for that wiggling to go away, because eventually, with friction and other things, it's going to go away. And right now, when he's running it with just the chair on it, he's calibrating it so that they'll know exactly how much it's going to wiggle and how long it's going to take to stop wiggling.
So he's got to go through the whole cycle until it's
Nope, he doesn't have to go through the whole cycle. He just has to go for a little while, and the computer will extrapolate to the whole cycle. Right? Then he gets on and adds some mass to it. There's an equation that will tell you how this thing is going to behave if you put a different mass on it. So you get on it with a different mass and you let it wiggle. And you observe how it wiggles, how fast it wiggles, and how long it takes for it to dampen out. And then you plug that stuff in the equation and out pops the mass. And that's how they measure the mass in space. So they're using the same technology, the same ideas, they're just using them a little differently. And they're not measuring weight, they're actually measuring mass. Because in the equation, it's the mass that determines, not the weight. This experiment will work anywhere. It will work on Earth, it will work on the moon, but we don't want to use a $25,000 scale in our house, so we use this one that costs me 50 cents. Right? Maybe. Maybe they paid me. So mass, different than weight, but there is a relationship. The weight is the amount of force that a mass feels when it's on a planet or a moon or something that's got a gravitational field pulling on it. Now, why does that matter to us? It matters because of Newton's second law. In Newton's second law, we learned something about what force does to a mass. In a word, forces accelerate masses. So when you have something that accelerates, some train or some ball or some whatever, and it's accelerating somehow, that acceleration is caused by a force. Now, if the forces are vectors. They have a magnitude and a direction. And if your force is pushing forward, like in this picture here, we get two people pushing, one person pushing on the wagon, one person pushing on the boy that's in the wagon. If your forces are all to the right, and you're accelerating that object, which direction do you think that object is accelerating? If all your forces are to the right? To the right. So, and that is kind of the idea, and that's important also to remember. And the way that we say that is we say that the acceleration points in the same direction as the net force. So the net force means you add all the forces together, including their directions. And you'll get a single force that is the sum of all of your forces, that is the overall force. And it will have a magnitude and a direction, and the direction of your net force is the direction of your acceleration. Does that mean that it's the direction of your movement? Why not? You're saying no. Why does the direction of the force not necessarily tell you which way something is moving? If it had an equal force back, then it wouldn't have a net force, right? Then those two would add together to be zero, and there would be zero net force. Let's think of a situation where something is experiencing a force, but it's not, that force is not causing it to move in the direction of the force. Is there a situation like that? Is there a kind of force that is not in the same direction as the movement of an object? Gravity, okay. That could be an example, but we need to think of the whole situation. That's not a situation, that's just a force, right? I'm sorry? Stopping your car, okay? When you're driving your car, I'm in my car right now, and I'm driving here east, right? So I'm driving east, and I stop my car. Which direction is the force that stops my car? Let's not even use brakes to stop my car. Let's use an object that I'm going to hit to stop my car. Okay? Which way is that force going to be on my car? Which way is it going to dent my car, for example? If I'm going this way, which way is the stopping force going to be? This way. But is the force making me go this way? No. It's just slowing me down from going that way. No, it's not neutral. It's a force that is this way, and I'm moving this way. In other words, forces do not have to point in the direction that you're moving. Now, you said gravity was a force that can do this. Well, how does gravity act on us when something is when something is moving in a different direction? I'm going to ask you the question right now. Which direction is the Earth moving relative to the sun? I'm sorry? It's moving in a circle around it. So its motion, is it moving toward the sun? No. Is it moving away from the sun? No. It's actually moving parallel to the sun, right? All the time. If you considered the sun to be a line, it would never touch that line. But it's not, it's a point. So it moves in this motion that is circular around it. We call the motion of this tangent, right? So if you drew a circle around the sun, then the Earth would be moving tangent to that circle. It's always moving along the edge of that circle, right? Its movement, its velocity is always pointing tangent to that circle. But what direction is the force from the sun pulling on the Earth with? What is the direction of the force of gravity that the Earth feels from the sun? Straight towards it, right? So this is the picture that we see. Here is the Earth. Here's the sun. Here is the Earth. Here is the path of the Earth's orbit. This is the direction of the Earth's velocity at any given point along this circle. If you put the Earth over here, then the Earth's movement would be this way. Okay? That's the direction of the velocity. Remember, velocity has to be a straight line vector. So it changes all the time. The velocity of the Earth is always changing because it's changing direction. It's not changing its speed, but it's always changing its direction. And what's causing it to change its direction all the time?
Falling towards it, missing.
The gravity of the sun is pulling it towards the sun every time. It tries to go off into space here, but gravity yanks it back into the circular path. And then it tries to go off into space again, and gravity yanks it back. It's like the Earth is on a string, and the string is constantly pulling it towards the center. It's like swinging a string around with a ball around your head. You always have to pull on that string to keep that ball in that circular motion. If you don't pull on the string, if you let go of it, what happens with that ball? Whoop, it goes flying off in a straight line somewhere. Right? So, the force of gravity is pulling on the Earth towards the sun all the time. No matter where the Earth is, that gravitational force is always towards the sun, and yet its motion is 90 degrees to that. Its motion has got a 90-degree angle to the force. So force does not have to be in the same direction as the movement, but it's always in the same direction as the acceleration. And we learned this a little while ago, that acceleration and velocity do not have to be pointing in the same directions. We have to remember it in this chapter because we're going to see it a lot in the coming chapters. Acceleration always points in the direction of the net force, but velocity, or the movement of it, does not always point in the direction of the net force. And that will trip you up, I promise. So try to remember it as much as possible. So what are all the forces that are acting on this wagon? We've got these two pushing forces, force 1 and force 2, but we've got these other like red vectors down here that are also forces. What are these forces down here? Okay, there's one force down here that is the force of gravity on the wagon from the Earth. Which one is it?
The arrow pointing down.
The arrow that's pointing down, what is it labeled with? A W for, why do you think they use W? For the weight, right? The weight of the wagon is the force that the Earth pulls on the wagon with. So that's the weight. And then what's this N force here? Anybody guess what that might be? Newton? Net? No. It's not Newton and it's not net. Does the wagon feel any force that pushes upward on it underneath the wagon? Let me give you a clue.
Is there a lever in the back tire after the lever?
Nope.
It's the support of the ground.
It's the support from the ground. If there was a force from gravity pulling down the wagon and there was no ground under the wagon, what would the wagon be doing? It would be falling, but is this wagon falling? No, it's sitting on the ground, and the ground is doing what to its wheels? Pushing up on those wheels to prevent the wagon from falling, right? It's the same with us. I'm standing here on the second floor of this building, and I'm grateful that there's a second floor to this building. Because if there wasn't, I would drop 20 feet to the floor and die, or break my legs, or something bad, right? So we call that the normal force. The force that something pushes on an object with to keep it from going through that object, keep going through a surface or a contact. We often call it a contact force as well. It's called the normal force, and they're showing that it acts on the wagon. It doesn't actually act on the wagon. It actually acts on the wheels. But we're going to show that all of our forces act on the center of objects for right now. We'll do it later. We'll do some more complex stuff, but we just assume that every force acts on the center of the object as if the object was a point. So this is a point wagon. Okay, imagine you have a wagon and you compact it to a point. All the forces act on the same point so that the wagon doesn't twist and turn. When things start twisting and turning, the math gets kind of painful. So we don't want them to twist and turn yet until we learn that math. So we draw a free body diagram. Our entire wagon becomes a point, and we have these forces acting on it. We have the weight force that acts down from that point. We have this normal force that acts up. Why do we call it the normal force? Normal means perpendicular in mathematical terms. So the normal force is always perpendicular to the contact point at where the two surfaces meet, or the two objects meet. It's always perpendicular to that point, to the tangent of the point where they meet. Then we also have the pushing forces from the two girls pushing. One boy, one girl. I don't know if they're two girls, whatever. Anyway, two people pushing the wagon. And then what's this force here? What's the force that's pushing backward on the wagon down here next to the wheel of the ground? Remember the car that's driving down the highway and runs into something and that causes it to slow down? What does a wagon always run into that makes it slow down? Air, ground, dirt, rocks, friction, right? And we usually use the little f to denote friction because friction is always present in just about everything. So we reserve the little f for our friction. So we've got a little friction one which points backwards here for our free body diagram. If you just have one person pushing, then you just have this one force out here instead of two forces. But these are what we call free body diagrams, and you should get used to drawing them because we will use them a lot. Every time you do a problem involving forces, you should draw a free body diagram. If you don't, and you come ask me a question, I will make you draw the diagram. Because until you know exactly all the forces that are acting on in a problem, and which direction they're pointing, and what their relative magnitudes are, and all this stuff, you can't solve a problem like this. Okay? So this is the first thing you should do. You should sketch out the problem and then draw a free body diagram. So one more thing to draw. Now, what did Newton discover? That's right. What Newton discovered is that force and acceleration are proportional to each other. If you add more force to an object, you get more acceleration with that object, right? But this was something that was kind of known. It was somewhat known. Galileo's work dropping bowling balls out of the Leaning Tower of Pisa helped them to understand that a little bit. Kepler's work with planets helped them understand it a little bit. But what Newton really did was the next step. He figured out the proportionality constant. He also discovered that acceleration is inversely proportional to the mass of the object. And then he put it all together and was able to show that the force, the net force on an object, is equal to the mass of the object times the acceleration of the object in vector form. You can also write it as the acceleration of an object is equal to the force, the net force on the object divided by its mass. Either way, it's still the same law. And this is Newton's second law. Quite easily his most famous law, and very likely his most useful law. Maybe most used law. The third law is also quite useful. Now, remember, what did we say? What did we say about laws when we were talking about physics in the first chapter? What is a law in science?
Proven right in the substance is
Sorry, what's that?
something that's been proven right in the
Okay, proven is probably the wrong word. Probably a better word is shown or observed, right? It's been shown to be true so many times that we assume it to be absolutely true, always true, right? Generally true. So that is the case with this. What Newton did is he didn't go out and mathematically prove this to be true. When you prove something, you have to show that it's true both experimentally and mathematically, so that you prove that it's true from other given laws and other assumed truths and other things like that. But this is a law, and that's usually what we call a theorem when you prove something is true. But a law is something that you show to be true through experiment and through observation again and again and again, and you've never seen it not be true. There is no situation where it's not true. And then you all of a sudden say, this is taciturn. This is a tacit assumption. We're going to assume that this is true all the time for everything, and we're going to build all of our theories from here. We're going to use this in every situation, assuming it's true, not ever assuming it's not true. And so far, it's never been proven to not be true. It is, as far as we know, still absolutely true.
Because, like, the only stuff we can do with the speed of light is X, I mean, mathematics,
Well, not necessarily. That used to be the case, especially back in Einstein's day. That was Einstein's problem, is that he couldn't do a lot of experiments with his theories because light is so difficult to deal with. We are much better at dealing with light now than we used to. So, but that's a different subject. We'll get into that subject next semester. So Newton's second law, force equals mass times acceleration. Notice that they have two versions of this. They have a vector version with the boldface force and boldface acceleration. Mass is not a vector. Mass is a scalar. Mass is just a number that tells you how much stuff is in something. It doesn't have any direction associated with it. It's just a number, and it's always positive. Not all scalar numbers are always positive, but mass is always positive. And then they have this version down here that is the scalar version of Newton's second law. This version right here implies that you have three different equations. One in the x direction, one in the y direction, and one in the z direction. One for each dimension, right? This bottom one is the equation that you'll have in each dimension. The net force in the x direction will equal the mass times the acceleration in the x direction. And it's true for the y direction and the z direction. So this is very similar to the velocities, where we can split our velocities in x and y, so v sub x, v sub y. We can split our forces into f sub x and f sub y, just like that.
So that's how to figure out all four sides of
Our acceleration in our dimensions.
yeah.
Yeah. So yeah, we will do it in pretty much the same mathematics. It'll just be with forces instead of velocities, forces and accelerations instead of velocities and directions. But we will use all that other stuff that we've done before as well. So what are the units of force? If force equals mass times acceleration, and acceleration is meters per second squared and mass is in kilograms, then our force is going to be mass, kilograms, times acceleration, meters per second squared, kilograms, meters per second squared. That's the unit. We give it a name, we call it the Newton, named after our good friend Newton. So, Isaac Newton gets a unit named after him. You know, that's what's normal for physicists. Physicists never really make any money, so we get things named after us instead. If we're famous and we do great things, we get things named after us. Then we die poor. Get buried in a pauper's grave. Right? rolls into a mass grave somewhere in Europe, like Mozart. And I don't think Newton was that way because Newton was a nobleman, but he was a knight. Anyway, so here is a very specific version of Newton's second law. This is the equation we use to calculate weight on the Earth. If you're on the Earth and you're near sea level, so near sea level means anywhere between 50,000 feet below sea level and 50,000 feet above sea level. So pretty much if you're on the surface of the Earth at all, this is going to be your weight. It's going to be your mass times the gravitational pull of the Earth, 9.8 meters per second squared. If you go up to the top of Mount Everest, which is 30,000 feet, approximately 29,900 something feet, you're going to lose a little bit of weight because you're further away from the sun, further away from the center of the Earth, so the gravitational pull is a little bit less there. The closer you get to the center of the Earth, a little bit more. Further away, a little bit less. But it's such a small percentage because the Earth, the height of Mount Everest above the Earth's surface compared to the radius of the Earth is tiny, like minuscule, like less than 1/100% or something crazy like that. It's just not very much. It's like 1,000 miles between the center of the Earth and the edge of the Earth, or more than that. I mean, it's huge. 30,000 feet's what, 6 miles? It's not very much. So it's just a tiny amount. But anyway, the point being is that what is the radius of the Earth? It's a lot more than 1,000 miles, but it's a lot.
Like 27,000.
Yeah, it's some big number. I don't know exactly what it is. I think it's like 8,000 actually is what
Oh,
it is.
you're talking about the radius.
Yeah, the radius of the Earth I think is 8,000 miles. The circumference I think is 20 something. But anyway, the point is that it's big and Everest is small, right? So it's a very small percentage, but the point is that if you're on the surface of the Earth, that's how you calculate your weight. If you already know your weight, that's how you calculate your mass. You just rearrange the equation and solve for m. You divide by g on both sides. So your weight divided by 9.8 is your mass. But this is going to be your weight in newtons. So let's do my weight in newtons. What's my weight in newtons? I already told you my mass is like 90-ish kilograms. So calculate my weight. I think my weight is actually, my mass is actually 95 kilograms or so. So put in 95 kilograms, what's my weight? So what is it? I'm sorry? Not 9.7, there should be a times 10 to the something there. So it should be, so I'm 95 kilograms times 9.8, which is what?
98.
Oh, there you go. So I'm 931 newtons. Do you know why we don't use newtons to measure our weight? Because people that are obsessed with their weight would be freaking out all the time. I'm 1,000 newtons, right? So we use pounds because there's about, for every newton, there's about 2.2, it's about, I want to say it's 2.2 newtons per pound. So that brings me down to about 200 pounds.
So you're actually putting the square root of 9.8?
Nope. It's just, you're just putting the mass, 95 times 9.8.
95.
Times 9.8. Yep. So essentially, if you measure your weight in pounds and then multiply it by 2.2, you'll get your weight in newtons. It is. But it works the same way. The 2.2 converts kilograms to pounds, but you should never convert kilograms to pounds because they're not measuring the same thing. That's like converting meters to gallons. It's not really proper to do that. Even though we do it a lot, it's not proper. Newtons measures weight. Pounds measures weight. Does anybody know what the measure of mass is in the English system? So if you went from pounds and you wanted to know the mass in the same units, the same kind of units, it's actually stones they use.
Oh, it's stone?
Yeah, it's stones, I believe. Is that, or is it slugs? Might be slugs. I think it's slugs, actually.
Or it's stone was like 20 pounds.
Yeah, slugs is what they use. So slugs are the unit of mass in the English system, but nobody uses them anymore. So newtons, the number of newtons is your weight. That's the amount of force that the Earth is pulling on you with. Your mass is your kilograms, which for me was 95 kilograms. So a 95 kilogram person weighs about 931 newtons on the Earth. That's how much force the Earth is pulling on you. So about 1,000 newtons is about 200 pounds of force.
So whenever we take that equation and spin it around, right? It's not W divided by D, there's W times.
No, if you were solving for mass, it would be W divided by G, right? So solving this equation for mass, this is what you get. This equation is force equals mass times acceleration. The force is the weight. Then if I wanted to solve for mass, I would divide both sides by G to get the mass by itself. And I would get mass equals weight divided by G. Right? But you have to know your weight in newtons, not in pounds, because we don't measure in pounds in physics. We measure in newtons. So let's say that your weight...
So you get your weight in newtons. How do you do that?
Yeah, so to get your weight in newtons, you have to know your mass, or you have to convert from pounds. And I'll tell you that in a second. So let's just say that you have, let's assume that you have a weight that's 500 newtons. Let's say you measured your weight on a scale, and the scale said 500 newtons, and you want to know what your mass is. You divide by 9.8 meters per second squared, which is G, and you're going to get, what do you get? 51 kilograms of mass when you do that, right? So you have 51 kilograms of mass. Well, let's say that you want to know, you know that you have 500 newtons of weight. That's your weight, and you want to know how much that is in pounds. Well, it turns out that there are 2.2 newtons per pound. So that's your conversion factor. Remember conversions from chapter 1?
It's
So-
not 2.2 though, that would make you 250 pounds and 51 kilograms. And if you said that you were 95 kilograms.
Oh, you're right. You're right. That's the wrong conversion. What is it then? What did you say it was? 0.225. Oh, yeah, that's right. It's 0.225. I got it. I got the wrong one. 0.225 pounds, newtons per pound?
Yeah.
Okay, yeah. Sorry, I had the wrong one. You're right. The one that I had up there was the fake one that goes from kilograms to pounds. Sorry about that.
Now, just how did you get to 931 newtons? That's what I want to know.
Well, for my mass, for my mass of 95 kilograms, that's my mass, right? So in the equation, weight equals mass times gravity. I plugged that in. I got 95 kilograms for my mass. G is 9.8 meters per second squared. So I plugged that in. Then I did the math. 95 times 9.8 is 931 newtons. Was it 931?
Yeah.
Yeah. So that's my weight in newtons using this scale.
So whenever we're using dealing with mass and weight, our mass is actually we put in our weight.
Our mass we're going to use to calculate our weight, right?
In newtons.
In newtons. Now we said that your weight was 500 newtons, but we don't really know how much that is in pounds. So let's find out how much it is in pounds. We have a conversion factor here that will convert from newtons to pounds and pounds to newtons. This is 225 over 1 pound. But I want to get rid of newtons and be left with pounds, so I'm going to take my 500 newtons and I'm going to multiply by something of this conversion factor. I'm going to flip it over because I want to get rid of newtons, so I'm going to have 1 pound over 0.225 newtons. So that my newtons go away and I'm left with pounds, right? So I need to take 500. Well, that can't be right.
I had to multiply it by 0.22.
No, this is pounds per newton, right? There we go. I had it backwards again. So we end up multiplying by this. We get 0.225 pounds per newton. The newtons cancel out, and then we multiply 500 by 0.225, and we get like what? 120? 112? So you're a cheerleader. Congratulations. Well, 112 is probably a little heavy for a cheerleader. But cheerleaders are like waifs that never eat anything, right? But they've got eating disorders. It kind of depends on your height and your build, I suppose. But I have no idea what it takes to be 112 pounds. It's been, since I was 10 years old.
Okay, so I took the 931 and divided it by pounds, which is 209, and got a 4.4545. Is that another constant or minus? I just was playing around.
I'm sorry, what?
I was playing around with the numbers and divided the 931 divided by 209. Just to
Yeah, and you got what?
I get 4.45 continuous.
So that would be 4.45, which is the inverse of this number, 0.225.
Okay,
So you just got you got the other conversion from newtons to pounds instead of pounds to newtons.
so that's
It would be 4.45 newtons per pound.
0.225 pounds per newton or 4.45.
Yeah. And the actual conversion is in the book or online or whatever. So if we look up online, if we go here and we look up the actual conversion, convert newtons, pounds, right? Then you get 0.224809. But if we go 1 Newton, then it's 4.44. 8. Right? Okay, so now let's move on to some other things with this, Newton's second law. Let's talk about an actual example of a force being applied to an object and accelerating it. We have a lawnmower here, and the lawnmower is being pushed by this man. The net force, the overall force, you add all the forces together and you get this overall force we call the net force forward, 51 newtons. Okay? Calculate the acceleration. I'll be back in a minute. Okay, what do you get?
2.125 meters per second.
They've given you the mass, they've given you the force.
Should be some meters per second squared, right?
What's that?
Should be meters per second squared.
It should be in meters per second squared. What did you do? You used Newton's second law that says the net force equals mass times the acceleration. You plug in your mass, right? Whatever it is, you plug in your force and you solve for acceleration. That's not the way we do things. We usually solve for the acceleration first. So we're going to divide by mass on both sides. Cancel over here, we're going to get acceleration equals force net over mass. Then we plug in our force, which was 51 newtons. What was our mass? Something 24 kilograms. Right? And we calculate our acceleration at 2 point, what did you get? 2.2? 2.125?
Now, do you always gotta go to the kilograms or newtons?
Yes, these are the standard units that we use. If it's in pounds, and they tell us that 51 newtons is about 11 pounds of force. So the force that the lawnmower feels, or the force that the man pushes with, is about 11 pounds. But if you plug in 11, it's not going to work, because those units don't mix. You have to use all the standard units together. Kilograms, newtons, meters, seconds, all those mix.
How do you do pounds? That's what you started with.
What's that?
That just turn pounds into newtons.
Yeah, so if they give you pounds, then you turn it into newtons. Convert it to newtons first, and then do the problem.
Now, can you turn it into kilograms?
No. Kilograms are mass.
Kilograms is mass, pounds is weight.
Pounds is force. Yep. Pounds is a...
Pounds to newton, kilograms to mass.
Yep. So, the acceleration ends up being 2.1 meters per second squared. Notice that the units do work out, because newtons are kilogram meters per second squared. The kilograms cancel and you end up with meters per second squared, just like you expect for an acceleration. Let's do another one. We have rocket sleds. This is actually a really cool video. Let's watch a rocket sled video. Trying to remember the name of the guy that did this. NASA rocket sled. Yeah. The U.S. Air Force Railroad. 8.5 G's of force. So if you take 1 G is 9.8, you multiply that by 8.5, and you get about 100 meters per second squared of acceleration. That is as fast as any person has ever accelerated and survived. Okay? So if you go any faster than that, you start to disintegrate things. Things start to fall apart and burn up, and you die. And human beings start to get squished. Let's check this out.
Once everybody else is asleep, and the writers are all out there by themselves, everybody, wow, what is this way? It's not making a countdown.
Check out that ambulance.
And the sirens are going off, the children how much drugs he had, and he'd be sitting there.
He strapped his helmet to the chair. That is a sweet ambulance. Ghostbusters.
You imagine hurtling down a track at the speed of sound and slamming to a stop in less than a second.
It's the stop that's the really bad part.
Damage almost every part of the body in these runs, and he made these runs over and over and over again, knowing what was going to happen.
Okay, so question. Why are the rockets configured the way that they are? You should know this just from what we've learned so far about forces. That one that's pointing up is holding the rocket sled on the tracks, right? It's keeping it on the tracks, keeping it from flying off the tracks. So there are a bunch of forces pushing it forward, but there's also one pushing it down, right? because air gets up underneath that rocket sled and pushes it up. So they have one to push the rocket sled down and keep it on the track.
Why do they make it stop so fast?
Because that's actually what they were testing. They weren't testing how fast he could go, they were testing how fast he could stop. The 8.5 times 9.8 meters per second of acceleration that he felt was not acceleration moving forward. It was acceleration stopping it. And they needed to know how much force a human body could tolerate. Because when they're coming in from space, they start decelerating. They get an acceleration backwards that's slowing them down. They're going 20,000 miles an hour when they're going around the Earth. That's dang fast. You know, it doesn't make any difference to them up in space. They're just cruising along, you know, whatever. But when they start hitting the atmosphere, when they come in the atmosphere, they slow down from 20,000 miles per hour to 200 miles per hour in a matter of a couple of minutes. That is an extreme acceleration. It gets up to 6 Gs, 7 Gs sometimes. But they had to know how fast they could decelerate them without killing the astronauts. So they did these tests to see, and they discovered that at about 9 Gs, 10 Gs, the human body starts to get in serious trouble. Internal organs start bleeding, things start bursting, breaking, things like that. At about 12 Gs, the rocket burns up. They discovered that as well. So they had to do these tests, and they still do them today. So, crazy stuff. Whew. Oh yeah, check that out. 128,000 feet, a parachute jump. That's incredible. Here's a guy that decelerated at 83 Gs. That's bad news. Okay, let's see, what were we doing? We were doing this. So here's our rocket sled. Our rocket sled is going to have thrust force, so we're going to call our force thrust now, and we're going to give it a capital T for its name. We often name forces different things instead of just force so that we can know which one is which, because we can have a lot of forces. We also have a weight force from the sled down, we have a normal force upward from the tracks, and we have a frictional force backwards. And then we know from this problem that the net force is going to be forward. These two forces are going to cancel each other out and equal to 0 down here. And the frictional force is really tiny compared to the thrust force. So we know the overall force is going to point forward, so the overall acceleration is going to point forward. And in this case, they're going to tell us that the acceleration is 49 meters per second squared and that the mass is 21 kilograms. They're actually telling us the acceleration and the mass, and they want to know the force. So we multiply the mass and the acceleration together, and we get the force. However, the force is not just one force. It comes from 4 different rockets, so there are 4 thrust forces, 4 times T, and then we have to subtract off the friction force because it's in the opposite direction. So the net force equals 4 times T minus friction. So mass times acceleration equals 4 times T minus friction, because mass times acceleration equals net force. So that's how you do your net force. You just add all the forces together and make a little function over here. And we want to know what is the actual thrust force, and they tell us the frictional force is 650 newtons. So we solve this equation for the thrust force. We add friction to both sides, and we get mass times acceleration plus friction. Then we have the thrust all by itself over here. And then we put in the numbers. The numbers for the acceleration is the 49 meters per second squared. The mass is 21 kilograms. The friction was 650 newtons given to us. So all these numbers were given in the problem. We plug them in. And that overall number, when we get it all put together, is 1 times 10 to the 5th newtons. And that's equal to our thrust times 4. 100,000 is equal to 4 times our thrust. So we divide that by 4, and we get, when we actually use the correct number, they're rounding right here, but the correct number is a little bit more than 100,000. And when we divide by that number not rounded off by 4, we get 2.6 times 10 to the 4 newtons of thrust for each one of the rockets. That's 26,000 newtons is not really a huge amount for a rocket thrust. It is a big number, but there are plenty of rockets that have more thrust than that. In fact, there are jet engines that have more thrust than that. A lot more. The jet engines on the F-15, I believe, had 25,000 pounds of thrust, and in newtons that would be 4 times as much, so at 100,000. So they had 4 times as much thrust for each one of those, and they put 2 of them on a jet that weighed almost nothing, so that the F-15 could actually go the speed of sound going straight up. And not only could it do that, but it could actually fly so fast that it would actually enter low Earth orbit. And they would fly these F-15s up into low Earth orbit till their engines would flame out because they had no oxygen up at 125,000 feet. They would flame out, and they put the little thruster rockets on them so they could maneuver themselves back to going down again so that they wouldn't lose control. But then they would actually fire a missile at that height to knock out low orbiting satellites. They used actual jet planes to shoot down satellites during the Cold War. It was kind of crazy. That was the incredible power of the GE engines on the F-15 McDonnell Douglas fighter. Did you have a question? Sorry? No question? No.
No. I just remember some buddies of mine quoting
Yep.
that for me.
It was an incredible airplane. They still use them. The F-15 is still the primary jet fighter of the Air Force. It's a great fighter.
A lot better than the F-16. I think $14 million longer.
The F-16 is not a fighter, so that's true. It's better than the F-16 as a fighter. As a bomber, the F-16 is pretty much unparalleled. But since the F-16 is a bomber, it has very different capabilities. It's not used as a fighter. Originally, they thought it would be a fighter, but it was just not powerful enough to be a fighter. Okay, anyway. Military technology is one of my hobbies. Unfortunately, some of the best technology out there is in the military. So if you really want to study cutting-edge technology, you kind of got to study the military. So that's interesting stuff. But anyway, here are some exercises where we calculate the external force of a sprinter. They give the acceleration of the mass. Then they tell us, then in this next problem, they tell us how far the sprinter sprints, the distance that they sprint, and then they tell us the acceleration from the previous problem and the mass from the previous problem, and then we have to calculate some things. We have to calculate, for example, the velocity that they hit. Well, that's a kinematics problem, right? So you go from a dynamics problem that involves forces and accelerations and mass to a kinematics problem that uses that acceleration to figure out how fast they actually end up going. So you're mixing kinematics and dynamics. So you don't ever get to forget your kinematics. And all these other problems are very similar to that, where they use dynamics, they use Newton's laws to figure out the acceleration, and then they use that acceleration in kinematics equations to figure out velocities, or distances, or whatever else. All right, so now we move on to Newton's third law of motion. Newton's third law of motion is actually fairly simple. This is what it is. It's simple, but sublime. It's something that's easy to forget and sometimes difficult to apply, difficult to realize what its implications are.
It's the normalization force.
What's that?
Is that the normalization force?
Not normalization, normal force. Normalization is a different word in physics, that's okay. The normal force. So whenever one body exerts a force on another body, that other body exerts an equal and opposite force on the body that exerted the force on it. And this is always true. But people don't always believe it. Okay? So my job right now is to help you people to believe that this is true. No matter what kind of force something applies on something else, the other thing always applies the same amount of force back in the opposite direction. Okay, let's take some examples. Some simple examples would be two cars that have the same mass, traveling the same speed in opposite directions, crash into each other. What is the evidence? They're just a head-on collision. What is the evidence that they exert the same amount of force on each other?
Therefore, a whole lot more than if that car going that speed would hit something standing still.
Well, let's not compare it to something else because that's going to get us in trouble. What is the evidence from the car crash, the head-on car crash, identical cars, head-on car crash, identical speeds? What's the evidence when you look at the car crash that they exerted the same amount of force on each other? Same damage, right? If they're exactly the same car going exactly the same speed, hit each other, it's going to be the same exact damage on either car. Guess what? If they're the same exact car, same exact size, and they're different speeds, it's still going to be the same exact amount of damage. If one of them's sitting still and one of them's moving at 50, it will be the same exact damage on both cars. In fact, it will be the same damage that you would see from both of them going 25 miles an hour and crashing into each other every time. That's one compelling piece of evidence that it doesn't matter if they're the same mass and they hit each other head on. It doesn't matter what their speeds are. They're going to have the same amount of damage. Now, why would it be different if they're different masses? Let's say it's a semi and a Volkswagen Beetle. Okay? 25 miles an hour, both of them. What's going to happen when you have 25 mile an hour cars and they're both Volkswagen Beetles and they hit each other? What's going to happen to their overall speed when they're done? If they have the same speed, they're going to stop. It's going to cancel out. But what happens if a semi is going 25 miles an hour? What kind of inertia does a semi have? A lot more. Is it going to slow down much compared to the Volkswagen? In fact, no, Volkswagen is not even going to slow down. It's going to stop and turn around and go the other direction. The semi is just going to keep going. Right? And what's going to happen to that Beetle? It's going to become a gnat instead of a beetle. And the semi is going to get a little bit of damage. The Beetle is going to be crushed. And everybody in it's going to be dead twice over. Okay? So let's go extreme. Well, let's talk about that one first. Why do we say that Newton's third law applies there? Did the Beetle apply the same amount of force to the truck as the truck applied to the Beetle? Newton's third law says it did. Newton says this is true all the time. Do we believe Newton or not? If you say no, then we got to reinvent physics. And we got a bigger job than we thought we did this semester. Right? So are we going to reinvent physics or are we going to try to explain this? I think I'm going to try to explain this. Right? So I'm going to say yes. But let's imagine you walk up to a semi-truck and you apply a force to it. Let's say we give 50 pounds of force with a baseball bat to a semi-truck. What's it going to do to a semi-truck? Let's not even use a baseball bat. A baseball bat's a bad example because it's going to dent them both the same. But let's say we have 50 pounds of force applied with a huge padded thing that's not going to dent the truck at all. It's just going to push the truck. 50 pounds of force, is it going to push the truck much? No. 50 pounds of truck, is it going to move the Volkswagen much? No, but more. 500 pounds of force. Semi-truck, is it going to do anything? Not much. 500 pounds of force to a Beetle, it's going to move that thing. The effect on the Beetle is different than the effect on the truck because of the mass. So if Newton's law is correct, the force on the Beetle is equal to the force on the truck. But on either side of this equation, you have the mass of the truck, force equals mass times acceleration, versus the mass of the Beetle. And if this is going to be true, according to Newton's law, mass times acceleration on the truck side is going to equal little acceleration, but on the Beetle side, it's going to equal what? A big acceleration. And acceleration equals damage. You know, like we accelerated the astronaut on the rocket sled, the more we accelerated him at the end of that ride, the more we damaged his internal organs. Well, the more you accelerate the Beetle, the more you're going to damage its internal organs, which are its passengers. and its external organs, which is the car. But the semi-truck never really got accelerated that much, so it's not going to have damage to the driver or the car or the truck very much.
This is a really odd. So theoretically, could you accelerate the Beetle to a point where its total force cancels out the impact? Like the total force cancels out the force of the semi. Like instead of you can't increase the
It always
mass of
does.
the Beetle.
It always does. That's exactly the point of this. The forces are equal. It does completely cancel out, except that it accelerates. I mean, the force that the Beetle exerts on the truck is equal to the force that the truck exerts on the Beetle. But those two forces aren't acting on one object. They're acting on separate objects, so it's not going to cancel out on the Beetle. The Beetle will still be accelerated, right? So this is the problem with Newton's third law when it comes to collisions, right? The problem is small things get accelerated a lot, big things get accelerated a little. Let me give you another example of this. When I was a swimmer in college, in high school, in college too, I didn't actually swim in college officially, but I did do some swimming in college, competitive swimming. But anyway, the point is that while I was a swimmer, a competitive swimmer, I would go to practice, and we were often doing kickboarding. It's one of the common things you do in practice all the time. It's like running lines or running laps in track, running lines in football, whatever. It's what you do to increase your heart rate when you're swimming. Normally, when you're swimming like with your head in the water, your heart rate doesn't increase. You're actually trying to lower your heart rate and not breathe very much. But still, you have to get some aerobic exercise as a swimmer. So you put a kickboard on them, they have to keep their head above water and breathe more regularly. So that's our aerobic, that's the only aerobic exercise you get swimming in a swimming pool is kickboard. So we did it a lot, but you get bored doing it and it's tiring and you're like, whatever. So what we would do is we would cheat while we were kickboarding. You do it circle swimming, so you got these lanes where swimmers are swimming on the right side of the lane going both directions. And as you're swimming by, you grab somebody's hand that's swimming the opposite direction and you pull, right? And each of you gets a little boost out of that. You're using strength and force from your arms to increase your speed there and give yourself a little acceleration. It's really nice. But it's much nicer for people who are lower mass. Why? They get bigger boost. If you have a small mass, because me and my best friend, we would do this, but he didn't like it so much. He was built like a tank. He had, just huge muscles and everything. He was a great swimmer. He swam in college. But he was this guy, right? I was this guy. So I would get this huge acceleration out of pulling. He would get a little accelerated, so it wasn't so fun for him. It was like, woo, I would go fly in the other direction. I would catch up to him, and he would just get this little thing out of it, right? So it's the same thing there. When I pulled on him and he pulled on me, it didn't matter what happened. We still got the same amount of pull, but our masses were so different that the accelerations were different, right? And that's why we don't believe it. That's why we say this law isn't true. You have two football players. You have a linebacker and you have a wide receiver. Your wide receiver is 175 pounds. Your linebacker is like 290 pounds or 500 pounds or whatever they are these days. They're just getting bigger and bigger. And the linebacker hits the wide receiver head on. What happens to the wide receiver? He goes flying like 15 yards, and they have to figure out where they hit him from the blood splatter on the field, because they just have no idea where they got hit. But the linebacker keeps going. He didn't even stop, right? That's because of the mass. It has nothing to do that the linebacker hit the wide receiver harder. He didn't. They hit each other with the same amount of force. Now, I'm going to give you one last test to help you believe this, because I'm sure some of you still don't believe it. I need a volunteer. Who's going to be my volunteer? You guys, okay, you need to be strong enough to break this tissue in half. So come on up here, Milo. I want you to break this in half. Karate chop it, man. Whatever. I need you to break it. Congratulations, you are stronger than a piece of tissue. I need another volunteer. I need someone else who can break a piece of tissue. Anybody else want to volunteer? All right, Brooke's going to be my volunteer. Now, Brooke is strong. She's going to break this piece of tissue. Go ahead and break this piece of tissue. Oh, she couldn't break it. Brooke's not strong. Brooke's not. Can you try again? Come on, Brooke, you need to break this tissue. So why can't she break the tissue? Because Milos and Brooke are the same strength. But I helped Milos. How did I help him break this? I applied a force to it as well. While Milos was pushing down, what was I doing? I was pushing up. And I was giving him help. He needed help to break the tissue. He needed my help, right? But Brooke didn't get any of my help. She had to do it all herself, right? And I wasn't applying that force. In order for you to break that tissue with no force acting, you're going to have to hit it a lot harder, right? Than he would have to, right? I cheated. I helped him. Because I was applying force in the opposite direction. So without that, it's really hard to break tissue because can tissue push back? Because the only thing pushing back is air friction, and that's not much force, right? To break that, you've got to have some serious force. And you have to hit it for a long distance, too, to break it. Okay? This is the reason, this is another reason that we roll with the punches when we're boxing, when we're in a fight, right? Because if you hit back with your head, it's like you're making the person hitting you hit harder. But if you don't allow them to hit hard, if you don't hit them back and you turn your head as they hit you, then you're not going to get hit very hard. This is why running backs spin when somebody tries to hit them. Somebody tries to tackle them, what do? They spin out of the way so that tackle doesn't knock them off their feet. So that they can keep their feet under them, so that force only moves their feet a little bit, and then they can keep running. It's not fancy, it's not getting out of the way, it's lessening the impact by not hitting back. If you hit back, you get hit harder, right? That is Newton's third law. Does everybody believe? Are we all believers? We have faith in Newton now? All right, amen. The Gospel of Newton. Here we go. What happens if the thing that you're pushing on doesn't move at all? Here we have a swimmer pushing off the wall. Does the wall move? Let's think more grandiose than just the wall of the swimmer. The wall's connected to what? Concrete deck. The deck's connected to the hip bone. No. It's connected to the earth. And does the earth move? Sure. Does it move much? I mean, talk about a mass discontinuity, you know? And not only does the earth not move much because it's got this huge mass compared to us, you know, compared to whatever we do on the earth, whenever we move on the earth, we're going to move the earth in the opposite direction every time. But the mass of the earth is so much bigger compared to our mass. And so its acceleration is so much smaller compared to our acceleration, right? So it doesn't even notice it. But not only that, but there's some guy in Australia doing exactly the opposite thing than we're doing. And pushing the earth in the other way. So it all cancels out. You know, when Milos goes home to Serbia, he's going to go push off the wall of a pool, and then somebody over in, where's 180 degrees from Serbia is probably Hawaii. Somebody in Hawaii is going to do the same thing there, but in the opposite direction. It all cancels out, and the earth just keeps spinning. The earth goes round and round forever, right? Doesn't affect the earth. Thank goodness. Okay. So, what happens when we get into more complex systems? Here is a complex system with lots of forces going on. We have to start thinking about defining our system. We have to start thinking, what is the system of interest? What is the thing that we're trying to do something with here? In this case, they've defined two systems of interest. If we're only interested in what's happening to this cart up here, then our system will be system 2, surrounded by this little green line here. And everything that's acting on this system from outside that green line will be an external force. And those will be the forces that will be acting on that system. So for system 2, the only forces acting are the frictional force, which act on the wheels from outside the system, the force from the professor, which is the pushing force from the professor, the weight of the cart downward, and the normal force from the floor pushing upward on the wheels of the cart. So 4 forces external to that system. If it's if we want to include the professor in our system, then we have a different force. The force the professor is pushing on the cart is no longer external to the system, it's internal to the system. And the cart pushes back on the professor as hard as the professor pushes on the cart, so that internal force, those two internal forces now cancel each other out. And that is true of all internal forces. If you have a system that is defined by saying this is the system of interest, you draw a line around whatever you do, then all the forces internal to that system are canceling out with each other, because there's always another force that is acting against the forces that are internal to the system. So the only things we care about are the things outside the system. In that case, then the foot of the professor is pushing against the floor backwards, pushing backwards this way. And which way is the floor pushing the professor's foot? Forward, which is why the professor moves forward, right? So as we push back, and you can tell that you're pushing back when you walk forward. It's kind of obvious. So you push backwards on the floor, and the floor pushes you forward, and that's what causes the motion forward. So we now have a new force which is pushing our system forward, which is the force from the floor on the system. Before it was just the force from the professor's hands pushing on the system. Now it's the force that the floor is pushing on the professor. And then we have our normal force and our weight and our frictional force, which are also external to the system. It is Newton's third law. The professor, when you walk forward, you're pushing backwards. You're pushing the floor backwards, right? So
Mass time acceleration.
it is, but Newton says that if I push the floor backwards to move forward, then the floor pushes me forward, because I'm pushing the floor backward, right? That's what Newton's third law says. If I do a force in one direction on something, that something will force me in the other direction, right? So that's exactly what's happening to push this system forward. Is the floor is actually pushing the system forward as the professor tries to push the floor backwards. The floor doesn't move hardly at all because it's connected to the earth. But the professor does move because they're much smaller mass. And if it's not making complete sense to you, just like always, be patient. It will. We'll give plenty more examples. This particular one is kind of it is an example. So let's actually do this. So we actually have some masses here. The mass of the professor, 65 kilograms. The mass of the cart, 12 kilograms. The mass of the equipment, 7 kilograms. So we might have to add some things together to get all the total mass. And then we want to calculate the acceleration produced when the professor exerts a backward force of 150 newtons on the floor. So that's the actual force that the professor pushes with to walk forward. They're pushing 150, she's pushing 150 newtons back, and we should then have an equal but opposite force from the floor pushing her forward. Then they also have the frictional force, which is a total of 24 newtons. So the equation, Newton's second law, rearranged for acceleration, is acceleration equals net force over mass. We need to add all of our forces together. Remember that forces have directions. The force from the floor is forward, which we're going to call positive. The force from friction is backwards, which we're going to call negative. So it's force of floor minus force of friction. We go ahead and calculate that net force to be 126 newtons from the numbers they give us. Then we have to have the total mass of the system. We're doing system 1, which is the entire thing, the professor, the cart, and the equipment. So we have the professor's mass, the cart's mass, and the equipment's mass. And this professor has a much, much lower mass than your instructor has. That's probably why she's a professor, because she takes better care of herself instead of the instructor. But anyway, total mass, 84 kilograms, and we plug those two numbers into our equation for the force, the net force, and the mass to get our acceleration of 1.5 meters per second squared. Now, if this professor continues to apply this amount of force the whole time, she's going to be going pretty quick after a while, right? After 1 second, she'll be going 1.5 meters every second, which is a reasonable speed. After 2 seconds, if she keeps doing this, she'll be going 3 meters per second. That's pretty fast. That's like, kind of rushing down the hall. But if she does it for 3 seconds, she'll be going 4.5 meters per second, which is kind of crazy going down a hallway with a cart. So Probably don't want to go quite that fast. If we choose the second system instead of the first system, then we have to choose a different set of forces and a different set of masses. It's still the same equations, still doing the same math here. They replace the force from the floor pushing the system forward with the force from the professor, and then they subtract off the friction. But it's the same process. In the end, you're going to plug them in to the equation after you've calculated the net force. And let's see, what are they actually wanting us to calculate in this one? Oh, they just want us to calculate the force from the professor. So that ends up being,
So her mass no longer comes into it.
I'm sorry?
Her mass no longer comes into it.
Her mass no longer comes into the second problem because she's external to the system. So you would subtract off her mass, and then the force now is the force from her hands pushing the cart forward. And that's actually what they want you to calculate here. You're going to take your, let's see what they do here. Yeah, so what they've done is they've taken the force from the professor and subtract off the friction to get the net force. Then this is the same stuff they did before. Then they calculated force of professor equals net force plus friction. And then they calculated the net force from the acceleration, the mass times acceleration. So they have the mass of the system is now 19. That's a different mass because they took off the mass of the professor, multiplied by the acceleration we got in the last problem to get the number of newtons of net force that's on the second system, and then they added the friction to that to get the force that the professor has to push with.
So friction's a negative number?
No, friction is a negative force. It's still just a positive number, but it's in the negative direction. But we added it to both sides, so it changed sign in the equation. Remember, the negative just tells you which way it is going, right? In the beginning. Okay, so let's do. Let's do the first problem here, the artillery shell problem. You guys work that out in groups. Get on the whiteboards, draw a picture, draw a force diagram. I want a picture and a force diagram. And then I want you to actually calculate and answer that question. I'll give you 5 minutes. Yeah, she said this. Does anybody want a Eclipse poster?
This is Newton's, right? It'll come out as Newton's. No.
Yeah. Yeah. Yes.
That right? Sounds too simple.
That is correct, but you didn't draw your picture yet.
I drew my, to get my,
You got your coordinate system
to figure it out.
Yeah, the calculation's easy. But I want to see a shell with a force on it, with an acceleration labeled, and all that stuff, you know?
Uh-huh. But,
So in this problem, it didn't mention any friction, so we don't necessarily have to put friction on there, right? And also, normal forces only exist if it's sitting. Is this showing you sitting? They fire it, right? So there's no normal force. The weight is there. The weight force will still feel. So this trailer showed a shot straight this way. They didn't say which way it was shot, so that's not right. Unless this way is actually this way, and it just shows you. But that's exactly right. There are two forces. One, and you don't really know which direction this was. They didn't tell us which direction this was. But this one always did. So we could draw it. Yeah, you could draw that angle or almost screw it up, whatever. Okay, so what forces are on this thing? You draw a force vector. You have a force vector that's firing. Which direction is that force vector moving? Which way is it firing? It looks like it's firing this way. Right? So the force vector would be right there. Label that with F. Right? There you go. Now there's one other force that's acting on this, and that's the weight of the down. So the draw one that pulls down towards you.
that's here.
No, it acts on the.
Oh, you want this to be the center.
Yeah,
Okay.
sure. But it doesn't matter where your coordinates don't have to be. The coordinates can still be here. Coordinates don't have to. You put them wherever you want. They don't have to be at the center anyway.
Yeah, but you want the shell in the center, right?
No, it doesn't matter. Where the coordinates go is just where you choose. The shell can be shot from anywhere. Coordinates just say that's what I'm calling my 0 point.
Yeah, because you can actually make your coordinates like this, right?
But yeah, you can also put your coordinates over in inertia. It doesn't matter where your origin is. It just makes the measurements different. Just, instead of starting at 0, you just start at 5 miles or 17 miles. So it doesn't matter where you start your coordinates at. The shell can start from anywhere it wants to. But you do have a weight that pulls the shell down, and you have a force that's shooting the shell up this way. There you go. Right?
So does your vector always have to be 90 degrees off of your velocity?
No. No, your weight vector is always straight down. Your force vector, your net force vector is always in the direction of the acceleration.
Yeah.
The net force vector.
So this one would actually look like this.
That works.
Because this here would be the one. This, right?
Yeah, that works. Good. And we'll get a lot of experience doing this. Let's do some examples together. Okay. So section 4.5, 4.6, and 4.7 are just all about examples. So we're just going to do as many examples as we can really quick. And then when we come back on Tuesday, we'll look over the homework. Hopefully you'll have enough time to get a lot of it done. And then we'll move on, if we can, on Thursday to chapter 5. So let's do some examples. We already talked about what the normal force is. Now, let's talk about normal forces that are not, for lack of a better word, normal. Let's talk about some abnormal normal forces, right? Here is a very simple normal force. You have your bag of bow wow chow, and you put it down on a table. And the table reacts with a normal. Now, while I'm holding it in my hands, there's no force, there's no normal force holding the bag up. It's the force from my hands that are holding the bag up, and the weight of the bag that pulls the bag down, right? And as long as that bag isn't accelerating, it could be stopped, I could just be holding it there, or it could be moving in a constant velocity. Remember that moving at a constant velocity has no acceleration. So if I'm moving that bag upward at a constant velocity and not speeding it up or slowing it down, then there's no force on it. It doesn't require any force to move something at a constant velocity. So there's no acceleration, there's no force. But if I sit it on the table then the normal force from the table, as long as the table doesn't break, the normal force from the table is now going to counteract the weight force and cancel those forces out so that the net force is zero, so the bow wow chow doesn't go anywhere. Okay, so in these cases, the normal force is simple. It's just equal and opposite to the weight of the thing sitting on the table. And that is always the case when you just sit something down on a level surface, horizontal level surface, and just sit it there and leave it there. Do nothing to it, just sit there and leave it there. That's always the case. You will get a normal force that is equal and opposite to the weight. If I come up to this bow wow chow after it's sitting on the table and I press down on it, I'm adding force to the weight of the bow wow chow. In fact, I could push down hard enough maybe to break the table so that the normal force is increasing to the point that the table can't push back enough to hold that bow wow chow up. So you can increase the normal force by adding extra force to the weight, by pushing down on it, for example. Right? And that wouldn't add to the weight of the bow wow chow, but it does add to the normal force. In that case, the normal force is greater than the weight of the bag because it's equal to the weight of the bag plus the force that I'm pushing down on it with. So that's one example of where the normal force and the weight aren't equal. But there are other examples where the normal force and the weight aren't equal. If I go up to this table and I lift up on the bow wow chow without actually lifting it off the table, I just kind of lift up on it a little bit, not enough force to lift the whole bag, but take some of the weight away from the table, essentially. So now some of the weight is being supported by my hands. The normal force on the table is not going to be as great. And we know what that's like. You've got a big heavy thing and you go to put on one of those flimsy card tables and you can see when you're starting to lay it down that card table is not going to hold it. And so you don't let all the weight go, right? You hold on to it and say, somebody give me a different table or something, you know. That's the idea there. Sometimes you know that that's the case, that you're actually decreasing the normal force that's required to hold up that bag by lifting up on it. But here's another one that's very common in the real world. What if the surface that you're sitting on is not parallel to the ground, not horizontal, not level? So here's a skier. This skier, ignore the problem itself. We're going to put a skier on the slope, and it's not level, of course. What happens to the skier if you put them on the slope? They go down. Why do they go down? Why is that different than the bow wow chow? Why didn't the bow wow chow slide off the table? Because the normal force and the weight force were equal and they canceled out. There was no more force left. You have to have a force to slide down the hill because they have to accelerate down the hill. A skier has to have a force in order to push them down the hill. So if they put it at an angle, now the normal force is pointing which direction? Instead of pointing straight down, it's pointing normal to the surface between the skis and the ground.
All right, so
that is perpendicular.
That's my question then, like on this. You're not firing shell straight, right? You're firing at an angle.
But it doesn't matter because there's no normal force on that shell. It's not sitting on anything. In order for a normal force to be there, it has to be sitting on something.
And we're not counting wind. We got-
No, normal force is when you have contact with two surfaces.
So is normal force calculated by like a mixture of gravity and friction in some way?
Yes, and we're going to see that in this problem. In this particular problem, normal force is calculated differently than it would be in other problems because it's a little more complicated. Normally, I hate to use that word, but often, like in the problem with the bow wow chow, you just calculate the normal force by saying what's the weight of the bow wow chow, right? Because they're equal in opposite directions. So you find out the weight of the bag, and that's equal to the normal force. You just say it's in the opposite direction. That's easy to calculate. But on this one, it's not easy to calculate because the weight of the skier is still pointing down. This is the weight of the skier pointing down. But the normal force is pointing this way. This vector and this vector cannot cancel each other out. They're pointing in different directions. If you're pointing in different directions, you cannot cancel each other out.
So there's force left over.
That's right. There is weight force that is left over. What we do...
Now, if friction equals
Let's get to the friction in just a second. Let's not talk about the friction yet. Let's first talk about the normal force. Okay? So, this is the weight of the skier going straight down. We know that there is a normal force that is perpendicular to the skis and the surface going this direction. We also know that there's a friction that is parallel to the surface and the skis this direction. So what we do is we create a new coordinate system. We've normally done x and y, x is vertical, y is horizontal, y is vertical, x is horizontal. That's been our normal system. But in this case, we're going to do a new system. We're going to call it the perpendicular parallel system. We're going to have one coordinate that goes parallel to our slope and one that goes perpendicular to our slope. So now we've rotated our coordinates. That's perfectly legal. The coordinates are not tied to anything. We can have the coordinates pointing any direction we want. And in this case, we want them to be parallel and perpendicular. So we have a new coordinate system. Okay? The coordinate system parallel is going to be positive going up the slope. For the perpendicular coordinate system, it's going to be positive going up away from the slope this direction. Now we have forces that are pointing in the perpendicular direction. We have the normal force in the perpendicular direction. We have the frictional force, which is pointing in the parallel direction completely. But our weight is pointing some other direction. It's pointing in between those two directions, right? So we need to resolve it into components. We need a perpendicular component for the weight, which is going to be perpendicular to the surface. That's this component. And we need a parallel component for the weight, which is going to point this direction. How do we know that these are pointing this direction? Well, we know that the weight is pointing down, and these two have to add together to equal that one. So a perpendicular one is going to be pointing down this way, and the weight one is going to have to go down to the left in order for it to match up with this one as we add them together. This is our free body diagram. Look up, everybody. The free body diagram has a friction that is pointing parallel to our surface. It has a normal force that is pointing perpendicular to our surface. It has a weight that is pointing off angle from both of those. And there is a perpendicular component and a parallel component. Perpendicular component, parallel component. These two components add together to equal the total weight. Now, from this picture, can you tell which force is going to cancel out the normal force now? Which one of these lines is going to cancel out the normal force? This one, right? The perpendicular component of the weight. So part of our weight cancels out the normal force, but not all of our weight. That's why the normal force is smaller, because only part of our weight creates that normal force, the necessity of that normal force. And this angle right here is 25 degrees, because this angle here is 25 degrees. If you want to work out the geometry of that, you can, you're welcome to. But let me give you a trick right now that you should pay attention to. Whenever you're going to tilt your coordinate system, because you're on some kind of a slope, make your angles extreme. So this is a 25-degree angle, and that's about what 25 degrees is, but I'm going to make it even more extreme so that I can always tell where my angle is. So let's go back to my picture here so we can see this board. So I've got a slanted coordinate system that I'm going to use. And I'm going to make the angle extreme. I'm going to make, here's my slanted coordinate system. Instead of making this angle 25 degrees, I'm going to make it like 5 degrees. I'm going to make one of these angles extremely small and the other one extremely big, right? So this is my angle theta or 25 or whatever it is. Then I'm going to go up here to my skier, and their weight is going downward, and I'm going to make a triangle with the perpendicular component and the parallel component of the weight. This is obviously the small angle, and this is obviously the big angle. Just like this is obviously the small angle, and this is obviously the big angle. If you don't make it extreme, it won't be obvious. Let me show you why. Let's say that this is my slope now, this is my ski slope. This angle and this angle look about the same. And then I put my skier on my slope, and I draw their weight straight down, and I draw my triangle. Which one is the 25? I can't tell, because I don't know which one was the small one, which one was the big one. You're going to have to do the geometry, and the geometry is a pain in the butt. You don't want to do the geometry. I do know for a fact, and I'm telling you this, you don't even have to work out the geometry, that if you do it this way, it will work, and you will always get the right angle. So this is my 25-degree angle, it's the small one, this is my small one, it's the 25-degree angle. Why do we care? Because this is now my weight that is perpendicular component. And it is adjacent to this 25-degree angle. So it's going to equal the weight times the cosine of 25. Now that's not usually what we do. This is an up and down thing. Usually we use the sine for up and down stuff, right? But it's different when we rotate it, and that's why you need to make sure you keep track of the geometry. And then this parallel component, the weight parallel component, which is this one that goes this way, is equal to the weight times the sine because it's opposite that. So that is why you need to remember these things. Okay? So, now we go back to, oh man, that's like all backwards writing on the screen, isn't it? Sorry about that. Let me see if I can flip that around. Nope, I can give myself a blockhead. Why can't I turn it around? Or I can do pop art. I thought there was one where I could flip it around. Bulge bend, twirl, stretch.
Mirror.
Mirror. No, that's a mirror down the middle. Normal. Nope, that's still backwards. I thought there was one where I could go. It's still backwards. Let's see, view, edit. It auto flips it after I think that after I stop recording it will auto flip it. If I started recording a video, but I didn't record a video. That's not very useful. Sorry, I'm sorry that these are all backwards. You'll have to read backwards. I'll have to figure out a new way to show my screen. I'll have to just find a camera program. But anyway, so here we are. We're back now to our problem here. We have our weight perpendicular, our weight parallel, and we're going to resolve these into components. We just did that where the weight perpendicular was the cosine of 25 degrees. That's this one right here. The weight, of course, is just mass times gravity, so it becomes mg times cosine 25. And then the weight parallel was mg sine 25, right? We did that already. But now we know that we can set up equations. We're going to set up equations just like we've done with kinematics. We're going to do it in the x direction and the y direction. Let's see if I can get a... Let's see. There's got to be a better way to do this. Well, I can just do it this way, I suppose. I can go to... Well, if I go to my screen recording and change it, it'll stop my screen recording. I don't want to do that either. I can do it through Zoom. I'll just do it through Zoom. I can do it through Zoom here. So change cameras, window, meeting, switch camera. Okay, so is that straight? No, it's also backwards. What's with the backwards camera thing? How do I change this?
Not a question. Is the recording still back?
Video settings. Enable mirror effect. There we go. That's better. Okay. Now it's correct. Is that correct now?
It's hard, we're out of time.
Yep. We're out of time. We are out of time, but let's do this really quick. Let's go back to our problem. There it is. So we go back up here to our problem, and now we can start to see the normal force is equal to the weight, perpendicular, and that's going to be our perpendicular direction. We used to do x and y, now we're going to do perpendicular parallel. So we go back to our screen really quick. Sorry to go over time. That's not where I want to go. I'm going to go to Zoom. Go to our screen really quick, and we're going to do two different problems. We're going to do a problem in the parallel direction and a problem in the perpendicular direction. We're going to set up forces equals mass times acceleration in those directions. So this is going to be the force net in the parallel direction. What forces do I have in the parallel direction? I have, in the parallel direction, I have the weight parallel, and that's pointing down this way, which is negative, so it's going to be negative weight parallel. And then I have the friction, which was pointing this direction. That's friction, and that's in the positive direction. Remember, these are my coordinates. Parallel and perpendicular. That's positive direction for parallel, so that would be plus friction. Those are my forces, and that has to equal the mass of the skier times the acceleration in the parallel direction. That's my equation. In the perpendicular direction, I'm going to have a new equation, a different equation. The force net in the perpendicular direction equals what's in the perpendicular direction. I have the weight of the skier in the perpendicular direction. That's going down, which is negative. So that's negative weight perpendicular. And then I have another force, which was the normal force up, plus normal force, right? And that has to equal mass times acceleration. But what's the acceleration in the parallel direction? Well, it's the acceleration of the skier going down the hill. What's the acceleration in the perpendicular direction? Is this skier going up and down on the, is he flying up the hill or sinking down into the snow? No. The acceleration in the perpendicular direction is 0. So this equation over here becomes 0, which is the acceleration times mass, equals negative weight perpendicular plus normal force. Solve this equation. Add the negative weight perpendicular to both sides, and you get weight perpendicular equals the normal, which we already knew. Right? The perpendicular part of the weight cancels out the normal force. That means they're equal. Right? On this side, we can use this side then to calculate some stuff, but on this side, we're going to have this equal to the acceleration of the skier. So we can calculate the actual acceleration of the skier. We will get back to that again some more on Tuesday, and but you should go ahead and do as much of the homework as you can before Tuesday, and then we'll work together on the problems that you struggle with on Tuesday, and then we will hopefully be able to get at least started on Chapter 5 next Thursday. All right? So have a good weekend. If you're going to stay here to do homework, I will be here for an hour and a half. I'm going out to lunch with my wife at 12:30, so. And Brooke, 3:45 today, right here, and we'll go over to talk to Rodrigo Verdi, who is our professor over there. He's a good guy. He's from Brazil. Yeah, he is. He's a really cool guy. Have a good one. All right, we're going to end this recording and post it online.